Every time you open a map app, an invisible electromagnetic pulse from space strikes your phone at exactly the speed of light. To figure out where you are, your phone receives a precise timestamp from 4 satellites in orbit. As this diagram shows, the math is strict. Distance equals the speed of light multiplied by the signal's travel time. Because light travels at nearly 300,000 kilometers per second, the margin for error is microscopic. A timing error of just 1 single nanosecond results in a location error of 30 centimeters. By resolving these time differences, your phone creates a coordinate map based on the most precise timekeeping ever achieved. But the system has a built-in conflict. The atomic clocks on those satellites do not tick at the same rate as the clocks on Earth. The clocks tick at different rates because orbital forces are physically warping the flow of time around the satellites. Failing to account for Albert Einstein's theories of relativity would cause these timing errors to accumulate, eventually making it impossible for the network to guide you through a city street. To maintain their position, GPS satellites must hurtle through the vacuum of space at nearly 14,000 kilometers per hour. According to special relativity, a clock in motion will tick slower relative to an observer who is standing still. This velocity causes the satellite's clock to lose 7.2 microseconds every single day, compared to a clock on the ground. At these orbital speeds, the satellite's experience of time lags behind our own. At the same time, those satellites are orbiting 20,200 kilometers above the Earth's surface. Einstein's theory of general relativity explains that gravity warps spacetime, meaning clocks in a weaker gravitational field, high above the planet, tick faster than those at the surface. Because the Earth's gravitational pull is weaker in orbit, the satellite clock gains 45.7 microseconds per day. This gravitational gain is constantly pushing the clock's time forward, directly opposing the slowing effect of its orbital speed. When you combine these effects, the gain from gravity wins out, leaving a net daily drift of 38.5 microseconds. Without a correction, that 38.5 microsecond error would translate into an 11-kilometer navigation error by the end of the day. To solve this, engineers apply a factory frequency offset, building the atomic clocks to tick slightly too slow in the lab on Earth. By launching clocks that are intentionally incorrect on the ground, they tick at the perfect frequency in the extreme environment of space. Even with perfectly tuned clocks, there is one final complication. The person holding the phone is standing on a rotating planet. During the fraction of a second the signal is in flight, the receiver on the ground is physically moving along with the Earth's spin. The Sagnac correction accounts for this motion. It calculates the exact area swept out by the signal to compensate for the fact that the receiver has shifted since the signal was first transmitted. Because the Earth rotates at hundreds of meters per second at the equator, a receiver can move dozens of meters while the signal is still traveling through the atmosphere. Pinpointing your phone within centimeters requires balancing orbital speed, gravitational time dilation, and the Earth's rotation. We achieve this by launching hardware into a mathematical environment that perfectly matches Einstein's predictions. Every time you use your phone to find a destination, you are using the most accurate validation of astrophysics ever put into practice.